Okay, I think I will just do a quick introduction. So my name is Violet Sia from EDB APJ Marketing, and our speaker today is Gabriele Bartolini. Gabriel hails all the way from Italy, and he is our VP for Cloud Native at EDB. Before we start, I have a few housekeeping items. Please note that the slides and recording for this session will be sent to you after the webinar. If you have any question, please write it in the Q&A box at the bottom of your screen, and all questions will be answered by Gabriel after his presentation. Okay, I will stop the poll now. Hi, Gabriel. I think the majority of people, about half of the attendees, say that they are just exploring Kubernetes now. And then quite a number, about a quarter, say that's click others. So I don't really know what that really signifies. And then we have 11% who says that they are planning to use it for stateless applications only. And another 14% say that they are planning to use it both for stateless and database workloads with PostgreSQL. Only 1% or 3% says that they are already using it for both stateless and database workloads with Postgres. So without further ado, let me then hand it over to Gabriel. Over to you, Gabriel.
Thank you, Violet. Yeah, I mean, the result doesn't surprise me. So, yeah, welcome everyone. So thanks for replying to this question. So where are we now in the cloud native journey? But most importantly, where do you plan to be in the future? So I think this is a very important question. And also, how do you feel about using Kubernetes to continuously deploy your stateless applications that talk to a PostgreSQL database? So only 1% is actually using Postgres and applications in production, and you know, this is something that we see often. Okay, and there's still this conception that databases can't be on Kubernetes. Okay, and hopefully, you know, by the end of this talk, everyone will get more confidence about using databases in a cloud native scenario, especially Postgres, as you know, that's been voted again as best database of the year in 2020 on DB ranking. So welcome to this webinar about cloud native PostgreSQL brought to you by EDB. My name is Gabriele Bartolini and I'm leading the cloud native initiative at EDB. And today I'll provide you with an overview of version 1.10 of Cloud Native Postgres, which is our operator for Postgres workloads in Kubernetes. So before I start, a short introduction about myself. I've been using Postgres for almost 20 years now, and I've been a member of the community for the last 15. Previously, I was with Second Quadrant, which has certainly represented the most significant part of my professional experience with Postgres. I joined the founder, Simon Riggs, in 2008 and covered several roles, including CEO of Second Quadrant Italy, Second Quadrant Australia, head of global support, and head of the lead and the Cloud Native initiative at Second Quadrant. I'm also one of the founding members and contributors of Barman, a popular backup and recovery tool for Postgres. And now I'm part of EDB, where I lead the Cloud Native initiative. So what is Cloud Native? Cloud Native is not just about tools. It's also about a culture that derives from DevOps and DevSecOps, lean, agile methodologies, and it's the outcomes in terms of processes, patterns, and tools. Cloud Native is about architectures based on microservices that rely on Linux containers. And when it comes to managing several containers and how they run on different hosts, Kubernetes is the de facto standard. Okay, but it's important to understand the role of containers and not confound that with cloud in general. Cloud native is a different topic. Okay, it's not. It could be also in private cloud on your Raspberry Pi. Okay, not just in the public cloud. So this is the agenda for today. After an introduction of Cloud Native Postgres, we'll go through some architectural aspects, operator capabilities, and configuration. We will then conclude with some information about storage. And I would like, if possible, to quickly go through a demo and maybe, questions, even reply to them after the talk, okay? So EDB is now the largest dedicated company that operates on Postgres in the world. EDB acquired the second quadrant, my previous company, in September 2020. So now, again, we are the largest PostgreSQL provider in the world. But we're also a member of both the Linux Foundation and Cloud Native Computing Foundation. And we are a Kubernetes certified service provider, KCSP. And we were the first Postgres company to reach this status. We build our container images based on Red Hat UBI images and publish them on key.io so that our software is also certified for Red Hat OpenShift, which is a distribution of Kubernetes supported and maintained by Red Hat. Our efforts are concentrated on two products: an operator for Postgres called Cloud Native Postgres, and an operator for BDR, which is multi-master revocation, called Cloud Native BDR. So we've just launched Cloud Native Postgres, which is a product entirely and exclusively designed for Kubernetes. It's a Kubernetes operator written directly in Golang and fully integrated with the Kubernetes API server. It relies solely on Kubernetes to manage high availability, and as such, we don't rely on external tools, which are also intended for traditional contexts like Rep Manager, Patroni, Stolon, or Failover Manager. We also build immutable application containers for Postgres 10 or higher, and for EDB Postgres Advanced 10 or higher. We're planning to release BDR later this year. So Cloud Native Postgres is a Kubernetes operator, but what is that exactly? An operator is an extension of the Kubernetes controller, and it defines how a complex application works in business continuity contexts. It simulates the work of a human operator in an automated and programmatic way. So specifically, we are interested in Postgres, and therefore Postgres is a very complex application. And an operator not only needs to deploy a cluster, which is the first step, but also properly react after unexpected events during the normal life cycle. The typical example is that of a failover. An operator relies on Kubernetes for capabilities like self-healing, scalability, high availability, updates, access, resource control, and so on. And it's designed to be fully automated and to support declarative configuration. So the easiest way for me to explain declarative configuration is through an example that highlights the differences with imperative configuration. In an imperative context, the state is defined as a series of tasks to be executed in sequence. So I can get a 3-node Postgres cluster by creating the first instance, configuring the replication, cloning a second instance, and the third one. In a declarative approach, the state of the system is instead defined using configuration. So in this case, there's a PostgreSQL 13 cluster with 2 replicas. This approach highly simplifies change management operations. And when these are stored in source control systems like Git, it enables the infrastructure as code capability and paradigm. And Kubernetes takes takes this further than deployment, as it makes sure that our request is fulfilled at any time. So this is important. It's not just a deploy time, it's for the whole duration and life cycle of a cluster. Why did I mention the concept of state? The reason is that it is the best way to explain why Kubernetes is so important to me. Kubernetes allows us to define as configuration the desired state of an object and a group of objects, and consequently the overall infrastructure, which is just several objects tied together. Kubernetes continuously makes sure that the current state of the infrastructure matches the desired one through reconciliation loops initiated by the Kubernetes controller. If the desired state and the actual state don't match, reconciliation loops trigger self-healing procedures. And this is where operators come into play. They need to define how these operations are done. So to clarify this concept, I want to describe what I would expect from Postgres operator through an example. So we request Kubernetes to deploy a new PostgreSQL 13 cluster with 2 replicas by defining a desired state. Then the controller, through reconciliation loops, detects that the current state 0 instances differs from the desired state 1 primary and 2 replicas, and invokes the Cloud Native Postgres operator to create the primary, then clone the first replica and then the second. So in case of failure of a standby, the reconciliation loop detects this event and initiates a self-healing procedure that either restarts the instance by reusing the same persistent volume or by recloning the entirely for more severe cases where the persistent volume was lost. Similarly, in case of failure of the primary, the operator promotes the most aligned replica and restarts the former primary as a standby by making it follow the new primary. The operator must also support scaling up and scaling down. So this is what we wanted when we started to think about Cloud Native Postgres, and that's how we ended up implementing it. So Cloud Native Postgres is an operator that implements the primary standby architecture of Postgres, so 1 primary and multiple standbys. Our operator has been designed to support custom application images, which enables to seamlessly work with either Postgres and EDB Postgres Advanced. Our containers are currently hosted on key.io and are generally available under the EDB limited user license. So I'm reading a question. Could you please show this demo on Linux servers? Please share a document if you have any for this setup on Linux. So yeah, the demo will be done on my Mac, but it's identical to Linux. Okay, so I'll go through the examples, and as you can see, there's a documentation that explains the exact steps I'll be doing, and you find it in these slides, docs.enterprisedb.io. If you go there, you find the whole documentation and even how to install the operator and the quick start. Okay, so in the traditional VM-based and mutable infrastructure mindset, we are used to think in terms of packages. Although we internally use packages to build our containers, the way software, and in particular immutable software, is distributed in Kubernetes is via container images. Our container images are built on Red Hat UBI 8, except that the EDB Postgres Advanced 10 and 11, which are on UBI 7. This means that we use our RPMs to install Postgres inside the containers. There are two types of container images that we distribute: the operator image, which is a Go application, and the operand image, which represents the application that the operator controls. So in our case, Postgres. At the moment, we build two families of application containers: the PostgreSQL ones, distributed under the Postgres license, and the GNU GPL3 license for Barman Cloud, and the EDB Postgres Advanced containers distributed under EDB Limited Use License. The Postgres container images are open source and provide also an entry point which enables rapid testing of Postgres in Docker. And by the way, we are launching these images in Docker Hub as well. So our goal is to run Postgres wherever Kubernetes runs. So by supporting all Kubernetes versions and Red Hat OpenShift, we are able to target private cloud and self-managed scenarios. By supporting Azure, AWS, and Google Cloud, we are able to cover the majority of public cloud scenarios. Google Cloud and AWS will be supported in Q2 2021. As a result, we want to introduce support for multi-cluster setups, opening up for both hybrid, as in public and private, and multi-cloud, as in multiple public cloud providers scenarios. So to recap this section, Cloud Native Postgres has been designed for Kubernetes and built on immutable application containers, which run only Postgres and are very, very light. We rely on declarative configuration, which is essential for the infrastructure as code paradigm. Deployments and interactions with the Postgres cluster go through the kubectl command line interface of Kubernetes, or OC if you use OpenShift, and YAML files to control the desired state. In terms of architectures, we can anticipate these two main architectures, okay, based on where the application resides. So if the application resides inside or outside Kubernetes. The first use case is the best experience of Cloud Native Postgres, as thanks to infrastructure abstraction, it creates an end-to-end highway between the developer and the end user of the application. It removes variability between development, staging, and production environments, and enables CI/CD pipelines at application level, including continuous deployment and delivery for high-performing organizations. Technically, the stateless application is managed as a deployment with an underlying replica set, and it is exposed externally through an ingress. The database is managed by the operator, which exposes a service to the application. We're talking about Kubernetes service. In the second use case, the applications reside outside the Kubernetes cluster. These are either legacy applications or applications that are in the process of being containerized. The application is hosted on traditional environments, and the database is exposed externally via TCP and TLS through an ingress. Cloud Native Postgres implements the primary standby architecture as we anticipated, with an arbitrary and optional number of hot standby streaming replicas, which are asynchronous by default, but can also be configured to be synchronous. Standby servers are required for high availability. Self-healing required us to introduce support for PG rewind in case after a failover, the timelines between the old primary and the new primary diverged. The cluster can also be accessed by the applications via 3 Kubernetes services that the operator transparently and automatically provides. One that points to the primary instance for read-write operations, one that points to the standby servers for read-only operations, and another one that points to all servers for read workloads. So, according to the operator capability levels framework defined by Red Hat for the operator SDK project, we are currently on stage 3 of 5, full life cycle, and we are aiming to reach level 4 later on this year, specifically the next quarter. Capability level 1 involves the installation and configuration of the operator. In this category, we include usability and user experience enhancements, as well as InfoSec matters. Capability level 2 is about enabling updates of the operator and the actual workload, so the Postgres server. This includes PostgreSQL minor release updates, which contain normally security and bug fixes, as well as major online upgrades, which is expected later on this year. Capability level 3 requires the operator to manage aspects of business continuity and scalability. Level 4 is about observability, so monitoring, alerting, trending, log processing, and this might involve the use of external tools such as Prometheus, Grafana, FluentBit, as well as extensions in the PostgreSQL engine for the output of error logs directly in JSON format, for example. Capability level 5 is focused on automated scaling, healing, and tuning through the discovery of anomalies and insights that emerged from the observability layer. We already implement some critical features at this level. In terms of cluster management, Cloud Native Postgres implements self-healing capabilities such as failover and replica creation through liveness and readiness probes, which are required by Kubernetes. The life cycle is completed with switchovers, rolling updates, and scaling capabilities. In terms of storage management, we support persistent volume claims, as well as storage classes for dynamic provisioning of storage. As a result, our users have complete freedom of choice and use any of the support storage in Kubernetes, both network and local. I will provide more details in the next section. So the only way to upgrade an application container is to replace it with an updated version of the image. As a result, a minor update of Postgres means that the container image of PostgreSQL 13.1, for example, is replaced with the 13.2.1 without touching the persistent volume. Cloud Native Postgres is designed to handle this kind of operation similar to Kubernetes deployments. It does that in a rolling upgrade fashion by first replacing one by one all the Postgres replicas, and then the old primary after switching over to a promoted and updated replica. Such switchover operation can be automated, which is the default, or manual. Rolling updates are also triggered when a change in Postgres configuration requires a restart, and they are the main reasons. One of the main reasons why we did not use replica sets and stateful sets in the first place when we designed Cloud Native Postgres. So as far as security is concerned, we adapted to the 4C security model of Kubernetes, which is performed at 4 layers: cloud, cluster, container, and code. You can find, if you look at our blog, you can find some articles about security and also about Cloud Native Postgres in general. So I encourage you to do so. We also support security context and pod security policies. It is important to understand that thanks to immutable application containers, we don't need root privileges to run our containers or to access volumes. And this is very important from a security point of view. We support TLS encryption and secrets. As far as source code is regarded, we systematically perform static code analysis in our pipelines, and our images are continuously scanned for vulnerabilities by key.io. So if you're familiar with TLS certificates, you know that that's a tedious and error-prone process. Cloud Native Postgres automates all of that for us by automatically creating a certification authority for the operator and one for each PostgreSQL cluster that we create. This enables us to turn on encrypted connections using TLS by default. But that's, this is just a start. We already support client authentication based on TLS certificates for our streaming replication standby servers. In version 1.1.0, we introduced the kubectl CMP plugin so that we can easily generate certificates for the applications. We are launching another blog article that explains this process. So we used all our 10+ year experience with Barman in designing backup and recovery support. We currently support continuous backup on object stores that are S3 compatible, both in public and private cloud. For example, relying on MinIO as a gateway. MinIO is an object store for Kubernetes. We rely on Barman Cloud Wall Archive for wall shipping by archive command and Barman Cloud Backup for scheduled and on-demand based backups. And this is all transparent, okay? As you've noticed, we don't support yet the full Barman, just the cloud utilities, but we're planning to change that in the future. Recovery is a way to bootstrap a new cluster by restoring from a previous backup, either fully until the end of the archive or up to a point in time. We do support all options available in PostgreSQL for point-in-time recovery. Even in this case, we currently rely on Barman Cloud, specifically Barman Cloud Restore and Wall Restore. The first one to uncompress the base backups, and the second one to pull wall files from the archive on demand. So now it's time to introduce the cluster resource, which is how we enable users to define a Postgres cluster in a declarative way. It is conceptually similar to if you are familiar with Kubernetes, to a deployment type, but it's also different because it embeds the primary and standby logic of Postgres. So it directly knows the internals of Postgres to promptly and correctly inform the Kubernetes API about the state of the entire Postgres cluster. This is, I think, the major difference between our operator and the available ones for Postgres in Kubernetes. The instances parameter defines the total number of instances, with instances -1 being the number of standby servers. We adopted the convention of a configuration paradigm, which, by the way, we had already successfully implemented in Barman. This YAML file is sufficient to create a PostgreSQL 13.2 cluster called myappdb, made up of 3 instances, so 1 primary and 2 standby servers, each with requested storage allocation of 10 GB, using the default storage class defined in the cluster. This is a very simple way to create a Postgres cluster. And how do we actually deploy that? So if you're familiar with Kubernetes, you would expect to simply use kubectl apply, and that's what we do. Okay, so you can install the operator with kubectl apply, pointing to the manifest URL of the operator, and you can install the cluster using the provided YAML file as definition. Okay, so through kubectl apply. So Postgres configuration must be managed by the parameters dictionary of the PostgreSQL map in the cluster specification. The operator has been designed to automatically manage reload and, if required, restart of the PostgreSQL instances following a change of the configuration parameters. Currently, the operator is able to correctly manage standby sensitive settings that must always have an equal or greater value than the primaries, such as max connections, max wall senders, and so on. But we will fix this in the next releases. By default, all replicas are configured in asynchronous streaming replication. However, you can configure streaming replication very easily using two parameters: min sync replicas, which is the minimum number of instances required to be in synchronous replication, and max sync replicas, which is the target value for reaching synchronous replication quota. By the way, this is how PostgreSQL works. Okay, so if you know, I don't know how familiar you are with these concepts, even the ones about continuous backup and recovery, but I suggest that you find information in the Postgres documentation. So the command line interface for cloud native Postgres is kubectl, and we have developed a plugin called CNP for kubectl that you can use to perform operations such as switchover, generation of TLS certificates, or even display the status of the cluster, like in this example. So as we are aware of, this is the only operator that does this kind of stuff for Postgres. In terms of storage, we know that storage is critical in a database context. We all expect that storage is always available, can scale, performs well, and guarantees both consistency and durability. So we as Postgres administrators normally associate availability of the storage with that of the hosting operating system. And scalability is achieved either via table spaces, LVM, or storage online resizing. As a result, when it comes to Postgres, we focus primarily on performance, which is one of the major sources of support requests, by the way, consistency and durability. Fortunately, when it comes to storage access patterns, the same concepts as in VM and bare metal environment are still valid in Kubernetes. We just need to integrate all this valuable knowledge with how Kubernetes manages storage. That is, storage classes, persistent volumes, and persistent volume claims. There are primarily two methods of access to storage. The first one is via network, either directly or indirectly. Think, for example, of an NFS volume attached to the VM hypervisor and used as a local volume in the virtual machine. Network storage is the most used pattern in Kubernetes, and there's a labyrinth of available solutions, either outside the Kubernetes cluster or inside the cluster. Normally, replication is at file system level, but again, network storage, even outside, even in traditional environments, is not recommended for Postgres, okay, because it presents the same issues of throughput and latency that we have all experienced. The second method of storage is the one local to the Kubernetes node where a pod is running. This also includes directly attached disks, which database people like us love. This is an anti-pattern in Kubernetes, but I've seen that the Kubernetes community is actually changing, and there's work happening in the shared nothing architecture direction with local persistent volumes and open source source products like OpenEBS or TopOLVM. We know the benefits of shared nothing architecture if you have been working with Postgres, but we also know the main limitation, which is easier scalability. So although there are several possible combinations and examples, due to time constraints for this webinar, I have selected two simplified architectures, one for network and one for local storage. The first one is an example of architecture of Postgres hosted on network storage using native stream replication for high availability. This is a portable scenario with cloud-native Postgres, but might not be recommended for high workloads that require predictability in performance. So if you're familiar again with Postgres in traditional environments, your existing knowledge on network storage databases can be directly applied to Kubernetes in the same way. So this is an example instead of local storage with Postgres replication, which is what we recommend for cloud-native Postgres. Thanks to the levels of abstraction and extensibility that Kubernetes provides, the same pattern is applicable in all contexts, both private and public. So preferably, we'd like to rely on disk that is not only locally mounted, but that is dedicated or even directly attached to the node where a Postgres pod is running. This means that we can implement the shared nothing architecture for Postgres even in Kubernetes, which is fundamental in very large database contexts. In fact, if needed, Kubernetes workload can be dedicated to a single Postgres cluster using its own dedicated hardware, a write controller with local SSD, or even its own SAN. So when at Second Quadrant, we pioneered the local storage use case for databases in Kubernetes. In May 2020, we published a blog article with file system benchmarks that became quite popular in the Kubernetes database community. We are planning to update it and rebrand it under EDB in the next weeks with also, new metrics, new numbers. The benchmark compared file system performance on bare metal with file systems in Kubernetes. Here we chose two configurations, local storage using the open source local persistent volume provided by OpenEBS, and network storage using CStore file system provided by OpenEBS. This is the dedicated hardware we use for tests. A Kubernetes cluster made up of 3 master nodes and 4 Kubernetes workers, each with 16 cores, 128 gigabytes of RAM, and hardware controller RAID with 2 RAID 1 volumes, one for the operating system and one for the applications, each with a pair of identical disks. We ran the performance test on the application disks, and the results went beyond our expectations. In terms of sequential reads, the bare metal test reached a throughput of 1 gigabyte per second, and the test inside Kubernetes approximately 960 megabytes, so only 3% lower than bare metal. It went even better in terms of sequential writes, where performance was almost identical, less than 1% overhead. As you can see, the performance of network storage, which is quite common in Kubernetes nowadays, is not even comparable to the local one, but we'll have to cope with this for I think a long time. So we went beyond that and ran OLTP-like tests on Postgres. So with just 2 physical solid-state drives, we were able to reach 3.8 thousand transactions per second against the 4.2 thousand we observed on bare metal. Again, you can appreciate the difference between the local setup that we are pioneering in Kubernetes and what we will probably be encountering more often in the next few years, which is an network storage. So the message here that is that we have opened a new frontier, and not only we can operate on standard and typical network storage setups in Kubernetes, but we opened up the possibility to use dedicated storage too, which is fundamental for very large databases and critical context, especially in the private cloud world. We have demonstrated that performance in Kubernetes is almost comparable to bare metal, with all the benefits of Kubernetes in terms of business continuity. And that's where we at ADB want to be. So the road ahead of us for Cloud Native Postgres is long, but we have a solid plan and commitment. We plan to improve logging and monitoring with a native Prometheus exporter that allows us to configure custom queries via config map or secrets on a cluster level. We already have a prototype for this, and we are planning to release that in the upcoming 1.2 version, either this week or early next week. We want to improve pooling facilities to address users with more strict performance requirements, as well as replication. For example, we want to be able to bootstrap a new cluster using Postgres, using another Postgres cluster inside or outside Kubernetes, having the same major release, and request for that cluster to operate in continuous recovery as a replica cluster. This allows for zero cutover time migrations to Kubernetes for Postgres 10 or higher, as well as the setup of replica clusters in different regions using cascading replication and independent backups. We also want to add support to logical replication, with an important use case being major online upgrades. As creators of Barman, we want to write a Barman operator that enables management of Barman in Kubernetes with transparent integration with clusters created with our operator. We also want to explore persistent volume snapshots for those storage classes that will support it. Finally, we need to explore the area of Kubernetes federation, where Kubernetes is working over multiple regions and coordinating different clusters. We know this is a hot topic in Kubernetes itself, and we will need to monitor how Kubernetes will solve this natively and then adapt. We're also looking to Rancher as well, which seems very promising in this area. In general, we will work continuously with product management at ADB to set the tempo, so also listen to what customers want and apply these the desired features according to the deadlines. So our software can be freely and independently evaluated by everyone. I read somebody asked about the ADB limited use license. So I'm going to answer now about this question. So essentially, we decided to differentiate between Postgres and ADB Postgres Advanced. So with Postgres, so if you plan to use your operator with the open source Postgres, you can start a new cluster without requesting a license key. So an implicit 30-day trial license key is created for that cluster. And after 30 days, all reconciliation loops will be stopped. Okay, so this means that you can use, even in your CI/CD pipelines or for testing, or even on your development environment, the operator with any supported Postgres, open source Postgres version without asking anything. And this, we think this is important, okay? Whereas if you're planning to use ADB Postgres Advanced, you needed an explicit trial license key to start the cluster. So you have to go to the website and register yourself, and you can download the license key that lasts 60 days from the day of issue. So we will introduce further options in the future. Okay, but essentially the limited use license is for ADB Postgres is that you can use it up to 60 days. And then to use it in production, you need a support plan. Okay, I hope that answers the question. So with Cloud Native Postgres, you can get the best of the two worlds. So use the extensive set of features that the community Postgres provides on the most advanced open source container orchestrator, which is Kubernetes. As a last remark, the key aspect to understand is that with Kubernetes, all applications coexist in the same distributed system. So when referring to applications, we include also databases, which are a special kind of applications or workloads that just require more attention on storage, okay? So my view here is that you can use databases, Postgres databases on Kubernetes, but you need to know Kubernetes very well to do that, okay? And this is not an easy step, you know, it requires a mindset change. So a change of mindset, you need to shift from the VM mindset to the container-based mindset, okay? And it's not, we cannot take this for granted, okay? It requires efforts from us. So if you worked enough with Postgres, you know how difficult it is to run a high availability cluster with automated failover triggering. Coordinating all the actors that provide the service to the end user is a complex series of simple tasks where each of these tasks can go wrong. Tasks that require different privileges and that might depend on components managed by different departments. So think about changing even DNS entries. So the risk of split brain, which is that is a set of applications writing to a Postgres database and another set to another database, is always behind the corner, and that's not easy to solve. So with Cloud Native Postgres, Kubernetes is the only authority and source of truth when it comes to management of cluster resources. If assisted by a good operator, it can make the whole business continuity management more reliable, ensuring that the Postgres database is always up, while hiding the complexity required for high availability of to the applications. At the same time, it controls the Postgres service, ensuring that applications speak to the database through a single interface. From a business point of view, knowing that applications can rely on Kubernetes to keep the PostgreSQL database up helps developers focus more on what they like to do more, develop. So at the same time, organizational and process waste is reduced through the implementation of capabilities that we have highlighted before, such as infrastructure abstraction, immutable application containers, CI/CD, and so on. This will increase development velocity and allow businesses to deliver more and more features to the end users and customers. So these concepts, that's the good thing of Kubernetes, can also be applied beyond Postgres, okay? Finally, relying on PostgreSQL and Kubernetes enables all of us to retain full control of the data that we process. So that also answer the question, what are the pros and cons of Postgres on Kubernetes versus PaaS and DBaaS from my perspective? This is certainly, I think, the most important one. And especially, you know, I come from Europe. GDPR became effective 3 years ago. And after that, we have put more awareness on where data resides. So Kubernetes and Postgres, I think, are an opportunity for all of us to get control back of the data that we process. Okay. So I'll try and set up, you know, a demo, quick demo environment. So yeah, I don't know, Violet, if you want to talk while I can. Let me see. Okay, you can see the screen here. So what I've done is I have created an empty cluster with kind. Okay, what's kind? Kind is a Kubernetes in Docker implementation. And if you look at the documentation, so I'm just going through the documentation of Cloud Native Postgres. Everyone can go here, docs.enterprisedb.io, installation. Sorry, quick start. So in the quick start, we suggest how to test the operator. And you can use Minikube or kind, or if you're planning to test on OpenShift CRC. I will use kind. Okay, kind is a very neat tool that everyone can use on their own laptop. It's essentially a Kubernetes distribution inside a Docker container. So I'll quickly launch. So this is what I did. I created the cluster called PG. As you can see, this is the command. So what I'm doing now, because it will take a bit of, a minute and a half, 2 minutes. Okay, now I will install the operator. So I go in the installation page. This is a command I need to run. So this command will install the operator in our system. I will copy this command. So I'm just showing you the operation that everyone can do independently just by following the documentation. And then what I'll do is here in the quick start, so I did install kind. I installed the operator. I will now deploy our cluster. So I've got this YAML file here called mycluster.yaml. I know that the latest version of Postgres now is 13.2, but I deliberately chose 13.1 because I want to show a rolling update. As you can see, there's many more options available, but I will use the convention of a configuration paradigm here. So basically, the operator will make opinionated decisions about the configuration of the Postgres cluster. But we believe, to start, they are fine. And I will actually split my screen in two. And below, I will execute a command, ccl get pods. And I will install the cluster. So as you can see, the operator is now, I put a watch on the pods. The first pod is actually a job, and it's the initdb job. So it's a process that at the end will be removed. It's initializing the primary, okay? I'll try and look at some questions in the meantime, because this will take probably around 2 minutes. So how GCP Kubernetes engine with autopilot cluster are simultaneously enabled for a fixed Postgres? That's okay. I need to answer this question after. I'm not an expert on GCP. Okay, so I'll take these and reply after. If Violet, you can take care of these. How TLS CA are redirected with Postgres Cloud Native Postgres running Google Cloud Kubernetes with its atomic database enabled. Again, this is something that I need to reply off the webinar. At the moment, we also we will support custom CA definitions. At the moment, we generate CA, I mean certification authorities for each cluster, but we will allow everyone to define the certificates directly before we create a cluster. So what are the pros and cons of Postgres on Kubernetes versus PaaS and DBaaS from your perspective? So I replied before about the retaining full control of data, but also, I mean, it depends on how familiar you are with Kubernetes. If you have, because that's where you will need people to manage the Kubernetes infrastructure. So if you've got very good knowledge about that, I suggest that you try with your own, even the self-managed Kubernetes on your premises. I've seen that lots of customers are going in that direction. Otherwise, you can use, for example, OpenShift if you still want to have private clouds, but you prefer to have a supported Kubernetes distribution, or you can go in the managed by the provider Kubernetes installations, like, for example, AKS from Azure, EKS from AWS, or GKE from Google. Okay. Otherwise, you can use RDS or other DBaaS solutions. Okay. But again, I think retaining full control of the data is an important reason. So is this feature of Kubernetes available only with EDB Postgres, or is applicable to open source Postgres? I don't know which feature we're talking about here. But all the features that I presented are available for both. So the only difference is EDB Postgres Advanced also introduces, for example, an Oracle compatibility layer. Okay. Does EDB offer managed services? Yeah, I mean, we will do that, okay, in the future. So we will come up also with the DBaaS offering in the future. Okay, how data availability is managed with local storage for Postgres in Kubernetes? Okay, that's of course, consider that you have a very large database and you want a predictability of performance. You can dedicate it, for example, 3 worker nodes to one cluster. Okay, so you have the physical machines with physical disks. If one breaks, of course, you need to replace that, but the imminent high availability is managed by Kubernetes. So by using the other 2, of course, you will need to go into the Kubernetes maintenance mode, so draining the node, fixing the node, the worker node, for example, the disk or the RAM or whatever happened, and bring it back. And if the persistent volume is still there, the Kubernetes operator will reuse it. So this is something that we are exploring. I think we are the first ones to explore this use case. But if you follow me, this will pretty much allow us to support everyone, from Raspberry Pis to public clouds, or even the largest database with dedicated storage. Okay. Yeah, you can definitely deploy Cloud Native Postgres in public cloud like AKS, and you can use any storage option available there. Okay, so yeah. Why compare with a database Cassandra? Okay, I mean, the difference here is that you will have all the benefits of Postgres. Okay, while for example, I'm not an expert of Cassandra, but I know PostgreSQL very well. So Cloud Native Postgres will allow you to use the full PostgreSQL on Kubernetes. Okay. So, okay, so now I go back to the demo. The cluster has been created. So what I'll do, I'll type this command, kubectl describe cluster example. So this is a PostgreSQL 13.1 cluster. And with these configuration options, the cluster is in a healthy state. You can get all the events here, okay? And these are the services that I was mentioning before. So, for example, kubectl get pods. These are the 3 pods that make up our cluster. These are their IPs. They're part of the pod network in Kubernetes. So now if I look at the services, for example, let's take the RW service. So right service cluster example RW, it tells me that these services, so the applications will use these, you see it's another network, this IP, but internally the endpoint is referencing the 08 IP address and port 5432. So the 08 is cluster 1. So that's our primary. I'll show you the CNP plugin. So you need to download that. It tells us that the primary is cluster example 1. Okay. So what I'll do now quickly is change the cluster and update it to version 13.2. So this is what you will do, when the new version of Postgres comes up. So we update the minor version and we apply again the change. Now, okay, in the bottom part, you see that the second standby has been shut down. So what's happening now is Kubernetes is downloading the image and is substituting the 13.1 image with the 13.2 and restarting it. Okay, so now we've got just one primary and one standby. See, cluster example 3 is down now. So the operation now will take, a few moments to conclude. Okay, I'll go through further question. Yeah, recording of this session. Yes, how to set up free trial license. Okay, so you go to the website, you download, you request the license, and this is how you, there's a parameter called license key, and you will need to add that to the cluster spec. Okay. By the way, here you will find several examples, okay, of configuration from the documentation. So, for example, here there's cluster example full. Here you will find all the available options. There's this parameter here called license key. Okay, so you need to do that. Okay, so everything is completed now. So we've got a new primary, which is number 2. So the switchover has taken place. And as you can see in the image in the panel below, cluster example 1 is coming up. So shortly it will be available. Okay, it's now available as a standby. So the rolling update, what it did, it first updated all the standbys and then switched over to the most aligned standby, which was cluster example 2, and then shut down the old primary and substituted the image. So what I'll do now and conclude this demo, I'll simulate a failover. I will delete the second pod, delete pod cluster example 2, force grace period. So this simulates hard shutdown of the machine. So the node where Postgres, the cluster example 2 is running goes down, okay, dies, okay. So as you can see below, the thing, the event was detected already. Cluster example 1 is the primary again. Cluster example 3 is now following example 1, and example 2 now has been restarted. So this is the end of the demo. Okay, the last. So I think I replied to the license, free trial license of Cloud Native Postgres. Maybe what I can do, you can go to the enterprisedb.com. Sorry, enterprisedb website, Cloud Native Postgres. Here is how you request a free trial. Okay, you can subscribe, and you can also get information about the plans and so on. This is, I think, an important example. If you go to the blog, this is a a blog article I wrote about immutable configuration, immutable application containers. There's also another interesting article for application developers. It's the first one of the series by our lead developer, Leonardo. It explains how to use Cloud Native Postgres on your local machine for development. Then, there will be follow-ups explaining how to use, for example, a specific language with Cloud Native Postgres. Okay, this blog article from scratch allows you to get up to speed with a sandbox environment for development. So PG pool to be supported, not at the moment. Okay, we are not planning to use Cloud Native Postgres, even though PG pool can be put on top of Cloud Native Postgres. Okay, so if you want, that's the beauty of Kubernetes as well. Okay, but at the moment we haven't done any testing, any benchmarking, and our choice is PG Bouncer. Okay. So yeah, I think I don't see any more questions.
Yeah, Gabriel, thank you so much. And thank you everyone for staying on. We are over the hour, but I really appreciate Gabriel's effort to try to answer as many questions as possible. Just know that we will send and share this recording as well as the slide deck to all of you who have registered and attended. So, and I will also include the links to the relevant blogs that Gabriel has mentioned. So once again, thank you so much for attending, and Gabriel, thank you so much for waking up early to do this for APJ. And we look forward to see all of you again in our next webinar next month. So thank you all and have a good day.
Thank you,
Thanks.
everyone.
Bye.
Bye-bye.
Bye. Bye.